This copper bus bar is the problem. 1 megawatt at 54 volts means roughly 18,500 amps. At 800 volts, the same ideal calculation is 1,250 amps. That 14.8 times current gap is why future AI rack power is being redesigned. But 800-volt direct current is not already standard across every data center. NVIDIA describes a transition for 1 megawatt racks and beyond, starting in 2027. We will trace the physics from busbar to chip, compare today's rack path with the proposed 800-volt path, examine the open compute sidecar, and show why protection becomes part of the architecture. By the end, you will know what higher voltage fixes, what it does not fix, and which claims an operator or investor should verify before treating 800 volts as inevitable. Start with one equation: power equals voltage times current. Hold power constant, raise voltage, and current falls. At 1 megawatt, the ideal current is about 18,500 amps at 54 volts and 1,250 at 800 volts. This is an electrical boundary before conversion losses, not a complete product claim. Lower current matters because resistive heating follows current squared times resistance. Real designers trade that margin among conductor size, run length, thermal limits, redundancy, and efficiency. The comparison must also stay honest. 54 volts remains useful near computing electronics, where it can be converted toward 12 volts in chip core voltages. The problem appears when rack power rises, until moving current through bus bars, connectors, and power shelves consumes too much space and thermal headroom. Voltage does not create energy. It changes how difficult that energy is to move. Locate 54 volts correctly. A conventional high-density data center does not send it from the utility entrance across the whole building. Medium voltage alternating current enters the site. Transformers, switchgear, and an uninterruptible power system condition and protect it. Alternating current then reaches the data hall. Inside or beside the compute rack, power supply units convert it to a rack-level direct current bus, often around 54 volts in the NVIDIA architecture discussed here. More converters step that bus toward 12 volts and the low core voltages used by processors. Each stage provides protection, regulation, ride-through, isolation, or load response. Each also occupies space, releases heat, and creates an efficiency and reliability boundary. NVIDIA says its current GB200 and GB300 NVL72 systems can use as many as 8 power shelves. Extend that pattern toward a megawatt, and power equipment begins crowding out compute. The proposed architecture moves the main alternating current to direct current conversion away from each compute rack. In NVIDIA diagram, medium voltage alternating current reaches a central power room, where large rectifiers produce an 800-volt direct current backbone. Protected busways carry it through the hall to the row and rack. Rack converters still step 800 volts down to 54 or 12 volts, then toward chip core voltage. The design does not eliminate conversion. It centralizes one stage and relocates bulky hardware outside the compute envelope. Lower current can shrink the distribution path for the same power, while fewer rack power supply modules can free units for accelerators and cooling. The diagram also exposes new work. Every boundary needs overcurrent protection, isolation, and safe service. This is a system redesign, not a voltage label. Its value depends on the complete utility-to-processor chain at the actual load profile. Existing buildings create a transition problem. Their halls use alternating current distribution, while future racks may want high-voltage direct current. One bridge is a sidecar power rack beside the compute rack. Open compute documents reveal an important naming detail. Diablo 400 produces plus 400 volts, a midpoint, and minus 400 volts. That is 800 volts rail to rail, but it is a 3-conductor topology, not automatically the same as every 2-conductor proposal. The May 2025 Diablo specification describes a concealed busbar designed for up to 1.1 megawatts of average load, with protected outputs in 50 or 100 kilowatt cable groups. The sidecar can hold rectifiers, optional storage, protection, control, and telemetry, while the adjacent rack keeps room for compute. This proves active standardization work, not that one topology has won or that sidecars are final. Higher voltage creates an efficiency opportunity, not an automatic result. Lower current can reduce conductor loss, and central conversion can remove repeated alternating current to direct current stages. But racks still need direct current conversion, protection, cooling, and redundancy. Their losses change with load and temperature. The Department of Energy's 2024 guide explains that conventional facilities perform multiple conversions because computing equipment and UPS batteries require direct current. It cites a 2007 Berkeley lab comparison in which a 380-volt direct current facility used 7% less energy than a typical 480-volt alternating current design. That supports the mechanism, but it is not a forecast for NVIDIA 800-volt system. A credible comparison must state the measurement boundary, loading range, redundancy, and cooling treatment. Vendor up to percentages are design targets, not universal operating cost promises. The physical prize is current capacity per unit of rack and conductor. NVIDIA estimates that a 1 megawatt rack on a 54-volt bus could require up to 200 kilograms of copper busbar. It also says power shelves could occupy up to 64 rack units in its future Kyber configuration, leaving no room for compute. Those are platform-specific NVIDIA estimates, not universal rules, but they expose the constraint. Busbars must carry current without excessive voltage drop or heat. Connectors face the same current at each mating surface. Parallel conductors add routing, current sharing, cooling, and assembly complexity. 800-volt distribution cuts ideal current almost 15 times, giving designers more room to balance conductor area and loss. Final copper reduction is not 15 times. It depends on length, insulation, fault rating, redundancy, temperature rise, and code. Voltage creates margin. Engineering decides how to spend it. The voltage that solves current raises protection stakes. Direct current has no natural zero crossing each cycle, so an arc can be harder to interrupt than an alternating current arc. Connectors, breakers, grounding, and fault detection must work as one system. The Open Compute Diablo specification makes the sequence concrete. It calls for current-limited outputs, concealed busbars, ground fault detection, and connectors that cannot be disengaged until a switch turns off power at source and load. A port should de-energize when unplugged, and load-side voltage must fall below the safety boundary on time. NVIDIA likewise places protection between the power room, hall, row, and rack, while acknowledging that overcurrent protection and serviceability need innovation. Central conversion may remove many small power supplies, but it changes the failure domain. Designers still need redundant feeds, selective isolation, telemetry, maintenance bypass, and proof that one fault cannot remove a compute row. When does this become real? NVIDIA says its 800-volt transition targets 1 megawatt racks and beyond starting in 2027. That is a roadmap, not today's installed fleet. The likely path is mixed. Existing alternating current facilities can add sidecar racks that convert locally to high-voltage direct current. New facilities can consider a native direct current backbone with central rectification. Compute racks can evolve toward direct 800-volt input as converters, protection, connectors, storage, and standards mature. Each step changes procurement and commissioning. Switchgear, battery strategy, grounding, controls, spare parts, training, and emergency procedures move with the voltage. A retrofit is not a cable swap. The economic case should compare specific old and new one-line diagrams at the same capacity, redundancy, load curve, and service level. Anything broader is marketing before engineering. Audit an 800-volt AI power proposal with 10 questions. What rack roadmap creates the need? Whereas 54 volts used today, inside the rack or across the facility, is the new topology 2-conductor 800 volts or plus and minus 400 volts with a midpoint? What is the current at design load? Which conversion stages disappear, move, or remain? Where was efficiency measured and at what load? How are faults detected, interrupted, and isolated before service? What redundancy remains after one rectifier, bus, cable, or converter fails? Where does ride-through storage connect, and what must it protect? Which parts exist now and which depend on the 2027 roadmap? These questions separate architecture from voltage slogan. 800 volts does not make 1 megawatt easy. It moves the hardest constraint from raw current toward conversion, protection, and system integration. The winning design must prove the complete path from grid to chip.